Yeah, thank you. So it's a pleasure again to be here and to give this talk. So this is about work which is very recent, actually not published yet, and that started when I was in Tokyo, actually 2 months ago. Started after discussions with Takato Yoshimura and the people who have recently published a paper, and I was looking at their formula and trying to understand their formula. So and it's so what is this work about? Basically, there's a general idea, a very conceptual idea, and we'll start with rather conceptual thing, a bit of mathematics, and we'll get a bit more concrete as we go along, up to some rather more concrete results. And it's about understanding, let's say, the various scales of hydrodynamics, and here are, the basic idea of these scales. At the thermodynamic level, you can calculate average of observables, and nothing move in space-time. If you go to ballistic transport, things start moving in space-time, so things are move, but still on very large scale. And then you could calculate, for instance, the due weight or things like that having to do with ballistic transport. But if things move on smaller scale, then you have to go a bit further, and then here you have the Onsager matrix. And the question is, can we organize observables or have some kind of structures that encode these various scales of hydrodynamics? That's kind of conceptual question behind that. So I'm going to be constructing certain Hilbert spaces, so not having to do with quantum mechanics, just some spaces of observables. You have observables and you organize in some spaces, you put some inner products, some Hilbert spaces, which represents these various scales. So there's a thermodynamic scale, ballistic scale, where you should see some particular Hilbert space, which corresponds to the conserved density, and diffusive scale, and this is the most interesting bit where I hope to kind of get certain results. And there's also, of course, intermediate scales. We've heard a lot about superdiffusion. So, in between ballistic and diffusive, there will be some superdiffusion things. So, and there's some Hilbert space you can construct for describing these things. Now, this is relatively abstract, but from these Hilbert space structures, by using appropriate projections mechanism, which we know in hydrodynamics, projections are very useful. We project over quantities that are long-lived. Now that's when people derive hydrodynamics, projections on long-lived degrees of freedom are something that's very fundamental. So using various projections, one can get results for these objects. In particular, I will show how to get results, for instance, as lower bounds for diffusion, lower bounds on the Sager matrix. And even going further, we'll be able to get a lower bound on superdiffusive exponent. And it turns out, in this particular setup, in particular when the diagonal G coupling, which appears in Herbert's fluctuating nonlinear fluctuating hydrodynamics, when this is non-zero, I do get a lower bound for superdiffusion, which is that of the KPZ universality class. So this is by analyzing these Hilbert spaces, basically. So I don't assume noise or anything like that, just analyzing Hilbert spaces. So this bound is relatively rigorous. This is much less rigorous, but nevertheless, just from Hilbert space analysis. Okay? So let me start with something that's very general. It's just some abstract construction. As I say, this start abstracts and then gets more concrete. Okay? So I'm thinking about some space of observables. So if you have a quantum chain, you look at the Pauli matrices on finite number of sites, for instance. But it doesn't need to be quantum. It can be classical, two lattice, now that. So, okay, some space of observables and some inner product on that space. So what kind of inner product can we choose? Well, there's a very well-known construction, this Gelfand-Nymark-Siegel construction in context of C-star algebra. Basically, it's very simple. You see the inner product is just the average of the product of two observables. One is complex conjugate or Hermitian conjugate. Okay? So either quantum or classical. And that has the right structure, is a sesquilinear, is positive semi-definite and all that. So that can be made into an inner product. And you can actually, so you have a set of observable, you have this positive semi-definite sesquilinear form. You can complete it, so you add the sequences that converge with respect to the norm induced by this form, and then you get a Hilbert space. This is just a little mathematical nicety, but it's actually useful to complete it if you want to do projection and have a Hilbert space. So you have some kind of inner product, and you have a set of observables. It's for now very abstract, but concretely in a model, you can write explicitly what these things are. It's just an average, right? Average of product of observables. And suppose we have also some one-parameter group of unitaries. So for instance, we may think about translations in space or translations in time. And these act on local observables, in a natural fashion when we have a local model. And if the state is invariant under these translations in space and time, then the resulting operator on that Hilbert space is going to be a unitary operator. And so we assume that there is some kind of one-parameter group of unitary. Okay? So, so for instance, space translation and time translation. So this is the abstract formulation. Then what do we do with this? So the idea is to kind of to find some operation that trivialize this one parameter group of transformations. So we want to take away space, things that change in space or things that change in time. Essentially, we want to look at large scales where things become homogeneous in space and time. That's kind of the basic idea. There are two ways of trivializing the space of observables. So you can just do something that one does in hydrodynamics, project over the things that are actually invariant under this other space or time transition, under this unitary group. Okay? So there's a projection from Hilbert space to invariant. You can write it in mathematics as intersection of the kernel of all these things. So everything that when you act with US on this observable, you get the observable again. So no change. Okay? Now, so this is some projection and denote like that. If you take for your US just space translation and your observables, the local observables, well, there isn't too much that is space translation invariant. In a typical quantum chain, the only thing that remains is the identity operator that is space translation. Everything actually changes in non-trivial fashion. So actually this takes a lot away from the Hilbert space. Here you would just get the identity operator. But you can do something else to take away, say, space translation invariance. You can do, so suppose you have something like some type of clustering. So you look at your inner product and you translate in space or time, you translate one of the observable, and you look what happened when you translate it very, very far from the other observables. These are local observables. So they should essentially cluster away. They should not know about each other anymore. So the conditions in a formal fashion that we write is simply that if I put this observable very far, according to this action of the group, then I should get basically the projection on the invariant of that group. Okay? That's a condition. Maybe it's satisfied, maybe not, but it's a condition. If this condition is satisfied, if the difference goes to 0 sufficiently fast, then you can just integrate over all this group action, integrate over space or time. And to make sure that the integral exists, you subtract this projection. You subtract the projection, and then you subtract the asymptotic. And when you do that, the result is such that you don't have any more this space or time translation invariant. You've integrated over it. So now any translation by US will be acting trivially. So you've kind of taken it away. A bit like projection, you've taken away, but here you've taken it away in a slightly different fashion. And one can show that this bilinear, this is a sesquilinear form again, or which integration over S. One can show this is also positive semi-definite. So this is good. So because you can write it as time and space or S and T integral of a product of things, and this is really the average of a product of two things. And if you look at A comma A, for instance, you're going to have an average of something square, and this is positive. So there's an argument to say this is positive semi-definite. And so from this sesquilinear form, you can form a new Hilbert space. Just look at all these observables, these A, under this action, and take away the null space, whatever it is. You form equivalence classes and complete by Cauchy completion. And you get what I call hydrodynamic reduction. You get a new Hilbert space, and on that Hilbert space, this US acts trivially because we've integrated over S. And the conserved charges, the Q of the previous one that we were considering, they are trivial also in it because we subtracted the projection over them. Okay? So you get some new Hilbert space and why not? There are two operations you can do. Now suppose I have space translation, time translation, and maybe a bit more, some higher flows, like in integrable models. There are higher flows in integrable models, right? So I can do all these operations. I can start with the Hilbert space of observables and project over the invariant. This is what I would call the thermodynamic space. Actually, this is a bit trivial because if you project over the invariant of space translation, you get indeed just the identity. So the projection is just the overlap with the identity, which is the average of the observables. So this space is just one-dimensional. It tells you about the average of observables. Nothing happened at a thermodynamic level. But then you can do this hydrodynamic reduction where you integrate out space translation. And once you've integrated out, you can project over the time invariant things. So you integrate out space translation and then do project over the time invariant thing. This is what I call the ballistic space. I'll show you why it's ballistic. But then you can go further. You can now do the hydrodynamic reduction with respect to time. So integrate over time. You get a new space. This new space now you can project over invariant under higher flows if there are any. If there aren't, then it doesn't matter. And you get what I call diffusive space. So let me explain why this is ballistic, this is diffusive. So the ballistic case, well, you know, so this, oh yes. So this is just some higher flow. I mean, you know, for instance, this Q3 that I was discussing in the integrable system. So this is, yes, I should have written. So there is an eta sub S which generates this flow. It might or might not be there, you know, but if it's there, it's. So the projection, this is projection on the space translation invariant stuff, then just get the identity operator. And this is integration over space translation invariance, and this is projection over time translation invariant stuff after having integrated. This is integration over time translation invariance, projection over whatever, higher flow invariant stuff. The idea, okay? And you can imagine you can continue that. Yeah. It's a very good question, and probably it has to do. I don't know exactly, but it is indeed right. I mean, this is what we do. We project out. Yes. So it's a bit difficult to write them explicitly because this is very abstract. So no, I don't know how to write them explicitly. But I can tell you, kind of, given some model, what kind of degree of freedom I have. So here, since I integrate over space, so I have things that are, say, total integral over space, right? So essentially, and now I look at things that are time invariant under this total integral over space. That would be the conserved quantities. So this is what it means, right? But now I integrate over time here at home. What do I get? Actually, I don't know. I don't know how to write that. It's formal construction. But I know I can do that. I start with some local degrees of freedom. I can do that, and can ask the question, what happens there? So for now, this doesn't give me anything. I think this your point. For now, this is abstract. Then eventually, I want to get something out of that. I will get something. Actually, I'll make this more precise. What are these things there? Okay? So, but what I want to say first about is this ballistic and diffusive thing. So, so certainly, if I subtract the invariant on the space translation, I really subtract just the average. And so, if I integrate over x, what I'm integrating is the connected two-point function, something that we've seen, of course. And that's my inner product. I should put a little dagger there. Sorry, I forgot. Inner product on the H prime space, right? And now if I look at the things in here that are invariant under time translation, then this is everything, so that if I try to do a dt of that thing, it's going to be a dx of this, because if you put a dx here, you get 0. So it turns out that this is indeed, you know, everything is sufficient. And so the ballistic thing, the ballistic space, which is everything invariant, is just all the conserved densities. This is conserved density. It's kind of a very simple thing, right? And then you can use this formal construction to write the Drude weight. So the Drude weight is integration over time of time evolution of a space integrated two-point function. This is what is written there. And if you take average over time, you just project over the time invariance of space, which is something that I showed in my lecture last week. And so you get just the kind of two-point function of the ballistic space. So it's just a formal rewriting of something that we know well. And then, of course, you get from this a hydrodynamic projection formula, the usual one, where the Drude weight is written as some projection over conserved densities, inverse matrix of the static covariance matrix, and projection over conserved density of the other operator. And this is a formula that is well known. So if you put the currents there, J, I, J, J, that's the B matrix, that's the inverse C matrix, and that's the B matrix. That's that we know. It's just a formal construction. But then the point is that, you see, the construction originally was completely abstract, so I couldn't have any Hilbert space, any one parameter group. And now I have this Hilbert space, H prime, which I construct like that, and I have a one parameter group of time translation. So I can apply the same procedure again. It's just this, okay? You apply the same procedure again, and you say, okay, now I subtract the projection over time translation invariance, which is just subtracting this sum over I, Qi, Cij, Qj, this particular projection. And then the integral over time of 1 minus projection of time evolved local observables gives me exactly the Green-Kubo type formula, why I integrate over x. This is this H prime thing, the connected correlation function. I've subtracted the weight, this is this projection, and I integrate over time. This is the Green-Kubo formula. Okay? So formally, you have this structure, it's a very formal construction that gives you the weight and Green-Kubo formula for the Onsager matrix. Now, for the Onsager matrix, I need to put the conserved currents there, the JI. It's possible to show, it's a little computation, it's actually not extremely useful in this talk, it's just a little nicety, that all these currents are actually they are actually in the diffusive space which I introduced, which is the space of invariance on the higher flows. So it turns out that these are kind of the conserved densities on in this higher space. They are invariant on the higher flows. And yes, the whole space. So our linear combination of these currents is included inside this. It's probably not the whole thing. I don't know the full structure. See, I don't know the full structure of that yet. And so that means the Onsager matrix can be written in the projection way, so it can really be written as an inner product on the diffusive space. And then if I'm lucky enough and I know a basis in that diffusive space, some stuff that is invariant on the higher flows, I can project again on that, and then I have an exact hydrodynamic projection formula for Onsager matrix. Right? Now this is if I know this basis, and a priori I don't know this basis. Right? So previously I kind of knew because these are the conserved densities. Now I don't necessarily know. Okay, so this is a formal construction. Now, of course, it may happen that the Onsager matrix is infinite, right? We can have superdiffusion. So it may happen that this large time limit, this time integral over all of R here, just does not exist. I cannot do this construction if it doesn't exist. Okay, it just fails. So what happens in that case? Well, so I can, very naively, but it's actually correct. Introduce some kind of different Hilbert spaces that go in between. I don't need to do the time integral over everything and without anything else. I can divide by appropriate power of the time interval, if I wish, just to make it finite, right? Of course, it depends how this diversion, all that. I can just choose the right U so that this is finite. So this space kind of lies between the ballistic and diffusive bit of these Hilbert spaces. And it's a simple matter to check that if we have some normal modes whose two-point functions have this kind of superdiffusive form for some exponent alpha, which may be diffusive or superdiffusive. If this is the case, then the current lies in the space H3 minus 2 alpha. It's just a little computation from conservation laws. Okay? So for alpha half will be diffusive, in which case we recover the diffusive space, but alpha greater than half will be superdiffusive, and then we have some other spaces. This thing. So basically, I want to define it as the space of all observables under which this limit is finite and non-zero. So that would be this. But it might be null. There might be nothing in it. But there might be something in it. And generically, for generic U, there is nothing in it. But for some U's, there might be something in it. And this is supposedly describing superdiffusion. Okay? Because we have this kind of... Okay, this is an abstract construction now. I try to be a bit more concrete, and this is the slide, although it looks a little bit abstract again, but this makes things a little bit more concrete. How to make things more concrete? Well, we have these observables, in this Hilbert space I define in abstract fashion. Now, I want to connect them with, like you were asking, what are these spaces I was telling you are. The ballistic space is the conserved quantity, the conserved charges, space integrated total integration of conserved densities, right? So I want to make that a bit more precise. So it turns out if you can relate this space with appropriately extensive conserved charges or extensive charges. And this is what allows us to get actual results. Okay? And what are these extensive charges? Well, suppose now I have some sequence of observable, which is supported on larger and larger number of sites. Okay? So Qn, they are local observables, but as n increase, they're less and less local. These are not at the end, it's not a local observable. The limit in n doesn't exist as an observable. And suppose I take away whatever the projection on the invariance that I'm interested in, and suppose it has these following properties: that it's the square, it's a square length, grows not more than n with some constant, smaller or equal, some constant n. Okay? And suppose that the limit at large n, if I take the overlap with some local observables, that this exists. The limit at large n exists if I take overlap with local observables. And suppose that this Qn is quite homogeneous. In other words, I look at n very large, and I look at A evolved by US or by UT, And the difference of that, is it goes to 0 when n is very large, and there's a precise formulation where you look at the supremum of that over some region in n, some region that is growing with n. Okay? Well, it turns out that the result, these maps to H prime defined in that way, they are in one-to-one correspondent with H prime, this space obtained by hydrodynamic reduction. So one can think about this weird H prime space as a space of action of charges that grow in a particular fashion. And so in other words, for every such map, there exists an element of H prime such that the action of the map is represented by the overlap in H prime. That's kind of this idea, yeah. So that means what you look at is so you have your charge supported on some space there. And you look at observable here minus observable there, and the action of that charge on these two things. You want this to be very small so that you can put the observable anywhere without changing the action of the charge. That's the idea, okay? And then sup mean you look at the supremum of all these differences when the position of the observable varies, say, from minus kn for some k to some other kn for some other k. Okay? And you want this supremum to go to 0. In other words, when n becomes large, all these differences become very, very, very small, really in a uniform fashion, become all very small. And so you get, in the end, invariance, you get homogeneity of this. And that makes sense because we know that in this space, we've taken away this translation by US, we've modded it out, so it should be homogeneous. Yeah, yes, possibly, yes. I haven't investigated, but yes, I think so. I think that there is a whole, you can also define things like that between ballistic and thermodynamics or something like that, yes. Probably related to critical phenomena, I think. The question. Okay, so you do that. So just as an example, I mean, if you just integrate over S between minus n and n, for example, you integrate over space between there and there, some local observable, that's an example of this linearly extensive charge. It's a very simple example, right? Because that integration over, over space from there to there, if you take the square of it, connected coefficient function, that will grow like n. And of course, if you act with this on some local observables, that will exist because you integrate over a large space by clustering. And so this is a simple example, and but this construction is kind of more general. It extends this simple example to a whole Hilbert space. And there is one set of calculations. Actually, the one crucial calculation in this whole thing is that why do you know that this Qn, this limit, is something that acts well on that Hilbert space? Why do we know that there is an element in that Hilbert space that represents it? And this is why do we assume it's corresponding with the Hilbert space? And that's obtained by bounding this thing. You look at this map, you want to make sure it's a bounded linear map on the space. It's this functional analysis stuff. And so you can bound it very simply. You say, well, this action by this homogeneity, by the supremum thing that I wrote, by homogeneity, I can just integrate this observable from minus kn to kn and divide by the volume, and that's the same thing. So I can just act on one fixed S, or I can integrate over S, and that's the same thing by homogeneity. And then I can bound this by using the Cauchy-Schwarz inequality. And when I bound that, so there's a square root of Qn, the length of Qn over 2kn, which is something that I said is finite. And then there's the square of this integral, which is something that I said goes to the inner product on the H prime Hilbert space. So the bound is given by some number times the length in this H prime Hilbert space, just kind of by construction. It's just a simple Cauchy-Schwarz inequality thing. And so what you find is that this map must be a continuous linear functional on that space. And as a consequence, by the Riesz representation theorem, there is an element B that represents this map by action by inner product on the Hilbert space. So this is interesting, but now you look at that, and this is something that we need want to calculate. This is related to the Drude weight, for instance, right? This length of is also related to the Onsager matrix. And we have Onsager matrix or something like that, greater or equal than something, and that's how you get these inner product, these lower bound. Okay, if I look at the space of linearly extensive charges on H, so just look at the space integral or the things that are supported on large space, on large regions in space, then what you get are what people have called quasi-local or pseudo-local charges that were introduced originally by Prosen some time ago and that are used to construct GGEs. So these Qn that I'm talking about, if I look at Qn on H to get something in H prime, this is what people, understand, use to construct GGEs. It's something that you can construct in quantum spin chains. But I want to go further here, and I want to do the same construction, not as linearly extensive charges on H, but rather on H prime. In other words, instead of integrating over X and taking things that are large in X, I integrate over T and take things that are large in T, where I have already kind of taken away the space translation. So I have look at linear extensive charge for H prime, which gives, by the general theorem, element of H double prime. It's because it was a complete general construction. So I know that my diffusive space has to do with these extensive charges on the ballistic space. So extensive charge in ballistic space give diffusive space. Now this is interesting because suppose I have some charge which I see as being supported on some region in space, and I want this to be a nice linearly extensive charge for H prime. Then there's a certain condition on the supremum of this time translation that I have to satisfy. And basically, if you think about it in terms of Lieb-Robinson bound, well, so this charge, if it's a conserved charge, from 0 to n, except for some boundaries, then the boundary effect will propagate with the Lieb-Robinson velocity. And this is the only thing that will prevent you from having homogeneity in time. So now you integrate over time. So the only thing that prevents you from having homogeneity in time is if you have something that's conserved, is propagation of Lieb-Robinson effects. And so you can set your k there exactly as 1 over 2 V Lieb-Robinson, and then you get an exact lower bound for diagonal Onsager matrix element, which is obtained by overlapping with this charge on the currents. This lower bound is something that Prosen had already obtained some time ago. Actually, this is a slightly improved version of his lower bound. It is framed here in the context of these Hilbert spaces, but it's something then that was already thought about. Now, these Qn, we need to, what are these Qn that we can construct? So here is an explicit example of some charge which is linearly extensive in H prime. So as I integrate over T. Okay? What is this charge? Well, take the ordinary conserved density, is the one that we know about, the conserved energy density or momentum density and all that. And consider the product of two such things, but integrated over X from minus n to n. So here I'm thinking of that in H prime, so there's no position anymore. I've integrated out the position. But I can multiply two things, and then there's a respective position between these two things. This is essentially the square. This is like a Qi times Qj, the square of the conserved charges, okay? But written in this Hilbert space. Well, it's simple to evaluate what is the action of that charge on any local observable. It's just given by a 3-point connected cohesion function, integrated connected cohesion function. This is just, abstract construction. Actually, you calculate that and it's very explicit. You just have to calculate a 3-point connected cohesion function where you have conserved charges inserted, which you can calculate just by differentiating with respect to the betas. This is a thermodynamic quantity, thermodynamic object. Okay? It's also simple to check how these charges grow. There's a particular gamma. And from this, we get an explicit lower bound, this lower bound, for the Onsager matrix. We know how the charges act on the current. We know the gamma. We know the Lieb-Robinson velocity. This is an explicit lower bound for the diagonal element of Onsager matrix, just obtained simply from the available conserved quantities that you know from your model. So if you know the hydrodynamics, if you know the thermodynamics, you know which conserved quantities you have, Hamiltonian, momentum, etc. And you can calculate this quantity, you can calculate that, and that gives you a lower bound for the Onsager matrix. So that tells you that if this 3-point function is non-zero, then you must have diffusion, right? You must have some non-zero Onsager matrix. Okay? So here it's kind of a bit more concrete because we have exactly the conserved quantities and things that we can calculate explicitly from thermodynamics. Now we can go a little bit further. So there is a relation that tells you how these conserved densities, which kind of the things that the boundary effects, how they propagate. In fact, if you choose a normal mode of hydrodynamics, they will just propagate at the normal mode velocities. So you don't need to take into account the Lieb-Robinson bound, but just really a precise velocity. And that's a relation that is true at the level of 3-point function. And that gives you a slightly stronger bound. So you have even stronger bound than the original frozen bound for on Sagawa matrix. So any questions about this? So I don't know, maybe I've lost, hopefully not too many of you. So one can go, I actually don't know how much time. Oh, you didn't start it. How much time do I have? I think we forgot. I have 35 minutes. Okay, well, I can slow down a little bit, yes. Okay. How much? 10 minutes, okay, thank you. I was very pleasantly surprised, but okay. Yes. Yes, okay, so, yeah. So you know, I'm not going into all the details. This argument, as I presented it, doesn't exactly line up with Tamash's argument, because Tamash was consulting slightly different extensive charges, which can also be connected to the H double prime that I'm talking about. It's a slightly different thing, but it's just a bit more complicated, actually. So it's about, well, so he had a bound about, actually, yes, is essentially related to curvature to the weight for sure, yes. But he basically had a general bound, which was saying if you have, I mean, basically that if you have a non-zero overlap between some extensive charges, some appropriately extensive charge, and current, then you must have a bound where the Liberation velocity appears in the denominator with some number there. But his charges are a bit different from the charges I've introduced here, a bit different. So this is, actually here I need a bit less assumptions than for his charges. He needed particular assumptions. Here I need a bit less of assumptions. It's a bit more rigorous, I would say. But still, I mean, similar level. So here I consider charges on the abstract H prime Hilbert space, while he was considering charges on the original space of observables. And then it gets a bit more complicated. No questions? Okay, so we have these particular charges. Now you can see these particular charges. So it's the equation between minus n and n of some local density qi, and then there's some other qj there. So there's something supported on n basically, and you can see that if you try to time evolve it, well, it's almost conserved. There's a conservation law, except for the boundaries. The boundaries will move around because you have boundary terms in this integral. And the boundaries, what I'm saying is that they move at these specific velocities. One can argue by linear response analysis that they move at these specific velocities. And so in fact, you can go a bit further than just saying that they move at these specific velocities. You can, so you see here you have a space integral 3-point function, space integrated 3-point function, basically, of conserved densities and other observables. But in the H double prime Hilbert space, it was time integrals that I had, not space integral. It was time integrals. How do I find the elements that represent this particular limit in the H prime Hilbert space, so that its time integral gives rise to the same form? So this is kind of an important question. What is the element in the Hilbert space that represents that? Well, you can use this picture, this result. And you can find exactly this element, which I call WRJ, which represents that large n limit. So there's an explicit element, observable, which is such that when I calculate its time integral, H double prime Hilbert space, I get exactly this particular space integrated 3-point function. And this element is just basically there's a factor coming from the Jacobian of transformation from space to time, and it has this in a completely explicit form. Again, there's this integration over x of qi qj that appears, but there's a difference of velocities, of the normal modes velocities that appear in front. And from that, I can obtain the orthogonality relation between these elements. And with this orthogonality relation, then I can obtain an exact projection over all these elements for the Onsager matrix. So I can see that the Onsager matrix is greater or equal as a matrix to some other matrix, which is just a projection onto that subspace of this particular element, which I call the wave scattering space. Okay? So this is relatively strong bound on the Onsager matrix, where you have a bound by quite a big subspace formed by all the ballistic all the conserved densities. So this is a particular subspace of the diffusive space, which is basically isomorphic to a product of ballistic spaces themselves. Intuitively, what it represents is kind of the scattering of these ballistic waves as they go around, and basically produce diffusion. That's the picture behind that. And this picture is actually something that people know from integrability. And in the end, this particular contribution to the Onsager matrix is the exact full contribution in the case of integrable system. There's nothing else in integrable system. And this this formula, this particular formula, is something that was obtained recently. There was a talk first week by Marco Medenjak, obtained by him, Jacopo Donardis, and Takato Yoshimura, by doing a slightly different construction where they expanded the current in a non-linear fluctuating hydrodynamics way up to second order and conserved densities. But here it's obtained by Hilbert spaces and seen to be a lower bound. Okay, so now what happens? So there's something interesting. So you see these elements that represent these particular these particular charges, they have zero overlap whenever I equals j or k equals l, or whenever two velocities are equal. So they are actually zero element. There is zero element in that Hilbert space whenever we have this equality. Okay? And then we can wonder, well, what happened if this limit for I, say, is non-zero on some particular element, yet the element that should represent it is zero. So what happens is very simple. It happens that if this coefficient is non-zero, then the corresponding element that we want to calculate in the Hilbert space is actually infinite. It has to be infinite. And so this Onsager matrix element has to be infinite. So from this argument, we see immediately that if a certain 3-point correlation function is non-zero, then there has to be an infinite Onsager matrix element, and hence there has to be superdiffusion. So just from this Hilbert space analysis. Okay? And this is also the case whenever you have two velocities that are equal to each other. Again, if this coefficient is non-zero, then this is infinite. And now we can make connection with nonlinear fluctuating hydrodynamics. This is nothing else but the diagonal G coupling that Herbert introduced. And if the diagonal G coupling is non-zero, with appropriate clusters of indices, the diagonal G coupling, then indeed you would expect to have superdiffusion. Here we just say, well, the Onsager matrix element, it has to be infinite. Can we go a bit further? Well, so we can go a bit further. I was introducing for you these fractional spaces. Okay? So it's possible to construct charges which are, instead of being linearly extensive, which are fractionally extensive. And so basically you make the same abstract construction, but you require that the homogeneity, say in space or in time, that it not be on some finite, window which is bounded by n, but rather some window which is bounded by some power of n, so that it goes much further up or down, say some curve like that. And if you require that, if you can find a charge that has this property, then it's possible to show that the action of this charge on an element is bounded by the norm of this element in the fractional Hilbert space, the one for superdiffusion. There's a bounding analysis that shows that this action must be bounded by that. And so now we obtain something like, this length in that fractional Hilbert space is bounded from below by some action of the charge. And so we can expect to have see something about superdiffusion. Okay? And it turns out that one can argue, and here it's not entirely rigorous, but it's from the natural phenomenology of superdiffusion. One can argue that these charge, so let me go back, these charge qi square, that gives something non-zero there, are exactly of this type. So these are charges where if I go back here, where you have the same conserved density here and there, and so naively this conserved density should be going at the same velocity. So naively, you should not have any bound on what time you can take in order to have some kind of homogeneity. But in fact, we say, well, in fact, it's not quite the linear velocity. There's a bit of diffusive or superdiffusive growth. So we assume there's some kind of growth of these boundaries, say, with some power alpha. And so basically, so the first thing that if there exists such a charge which is non-zero on the current, which we know it is Hilbert space 3 minus 2 alpha, then the fact that this current must be zero whenever this u is smaller than 3 minus 2 alpha imposes a lower bound for the alpha. So alpha must be greater than 3 minus u over 2. So if there exists such a charge with some mu, some fractional extensivity u, then there is a lower bound for the superdiffusive exponent. And indeed, we think, so it's clear that there must exist such a charge, and it's this QII charge. And this QII charge, we can bound U by U minus 1 greater than alpha. If you combine these bounds, you get exactly alpha greater or equal to 2/3. So the 2/3 bound comes from analysis of a fractionally extensive charges where the boundaries don't go at certain fixed velocity but grow in some power law like that. And the fact that the current has to be in a certain fractional Hilbert space by this 3 minus 2 alpha. Combining these two things, we get an explicit lower bound for the alpha that has to control the current, and this is indeed the KPZ lower bound. Yes. So if I come back to this, this is this charge, these charges, right? This product of charge, which act like that, right? And so you can understand them as being some, conserved charge with some boundary that expand in some way, that move in some way. But since this QII is the same mode, they will move at the same velocity. So if you think in terms of the, what kind of time you can take to have homogeneity, it should be infinite, and that will be a bit too strong. But it's not quite infinite. They move actually as superdiffusive with some superdiffusive exponent. And then so all you say is that there is some superdiffusive exponent by which they move, and there's some superdiffusive exponent which control the current, and both relate these things to various Hilbert spaces, and you impose this condition on these spaces. You want this, to have that this current will be 0 in certain Hilbert spaces and non-zero in others, and that this act non-trivial on that. You combine these things, and you obtain the lower bound for this alpha. Combine these two equations, kind of bound for this. What questions? Okay, so that's all I wanted to say. So there's a lot of small things one can do with this Hilbert space. One can understand these kind of quadratic charges as being covariant derivative on manifold of space. Okay, so here are some of the kind of additional questions one can have about that. I think there's nice things to be explored. Thank you for your attention.
Thank you. So, other questions? Yes, please, yeah.
Yes. So this lower bound. So whenever that 3-point coupling is non-zero, so like in non-linear fluctuating hydro, whenever this coupling is non-zero, then you expect that lower bound for that. The lower bound for Saga matrix is expected whenever you have E-Robinson bound and all that, and it's expected to have all these lower bounds are expected. So it's not, it shouldn't matter if it's a quantum or classical. So for instance, for the spin transport lower bound that you have been working on, one might be able to find some appropriate charge that make it non-zero, and that act non-zero on that, which has the appropriate kind of expansion, superdiffusive extension properties. And then we'll have the lower bound.
Maybe I may could add a question on this. I mean, so I take, let's say, one-dimensional system, and I focus on one specific conserved charge. And now, in principle, from a thermodynamic computation, I can look at the G coefficient, and let's say, I somehow can do this thermodynamic computation, and I find that this G coefficient is actually non-zero. Are you then predicting that sort of this lower bound, or are there sort of lots of other assumptions which are difficult to check?
So there are some assumptions which are difficult to check. So what are the assumptions that are introduced here? So the assumptions, well, there's the assumption that the thing that we see in hydrodynamics, that the 2-point function have a certain profile with a function that decays fast enough that grows with some exponent as a consequence of 2-point function. So that's the assumption, but it's relatively fine.
That's a static assumption, right? I mean,
yes,
but that I'm sort of willing to buy that your TGE is sort of sufficiently short range, so to speak.
Exactly, I mean, that's this. But then the important assumption is that assumption that goes into this drawing. So it comes back to here to the assumption. So it's an assumption about 3-point function, and their clustering properties. Okay? Okay. And the assumption is if you have some observable at xt and some conserved density at y0, z0.
This is a dynamic function now, right?
This is a function of xt.
Okay.
Yes. This is time dependent on that. This is not trivial.
Okay, that's fine. All right.
The assumption is that this will be clustering whenever this xt is far enough from some parabola expanding region around the position of these q's, with the parabola being the same as the one that you find in the two-point function expansion. That's the assumption.
Yes.
So do you have also sometimes upper bounds on the diffusion constant? Do you know that it's really diffusive and not?
Yeah, no, that's of course that's a very good question. That's super important, right? So do you know can you prove it's diffusive? For instance, I can kind of show it's super diffusive, but if I don't have that, I cannot show it's diffusive. I don't have an upper bound, the diffusion constant. In my formulation, you have to sum over the whole Hilbert space, and so basically you have to make sure that in whatever basis for the Hilbert space you have, this sum is convergent. It's a convergence thing. It's difficult.
And at some point you showed something where you have H prime, and corresponding to, I don't know, thermodynamic, ballistic, diffusive.
Yes.
And then I had the impression that it could be continued, right? Those
yes.
So
there's dots for a reason. Yes.
What can we imagine after diffusive?
So what I'm thinking, my thing about that is that if we have an infinite number of flows, of commuting flows, like in integral models, then we can continue this. And we should get the higher and higher powers and derivative expansion of the hydrodynamic equation, basically. So we should get to, I don't know how to call it, but like third order, fourth, fifth order, etc. And supposedly in an integrable system, you can get to all orders and get some kind of asymptotic expansion, not convergent, but asymptotic expansion. In free models, then it's actually convergent. It's probably the full thing. In integral models, it's some kind of asymptotic expansion. So this picture suggests that until where you can get with your hydrodynamics, derivative expansion is controlled by how many flows are available. So how many Hamiltonian flows are available. So suppose there's no more flows there, then probably hydrodynamic approximation breaks down beyond that. Something like that.
Any other question? Microphone.
So suppose I look at the hydrodynamic equation and I do the all-order derivative expansion. I calculate something with all-order derivative expansion. It's not completely clear to me that this, that this will give the right thing for any finite time, right? It's still an asymptotic at large time, or at, asymptotic with some large parameter, at some large parameters, but it's a full asymptotic expansion. The derivative expansion is correct as you go to large time in appropriate situation. So it seems to me that this will also be the case. I wouldn't expect that this gives the exact answer. Just.
Okay, any other question? That doesn't seem to, no.
Yes. That's a very good question. I think this is the thing that we're kind of thinking about now. I mean, some of these objects are these QI, QJ, these quadratic charge, which I call so some of these, right, is part of subspace, but there's more in general, right? What are these other things? Am I thinking about that? Is as follows? Yes. Yes, is that. So it's basically that, but it's just that there is a particular understanding of what some elements are, and they're basically Q square, this type of thing. So, and these are nice, and there's an interpretation of that as diffusion coming from the scattering of ballistic waves, and it's just interpretation, right? But then if you have an arbitrary system, hydrodynamic system, and you look at what can happen to the system, I mean, there's ballistic wave that can go around, but there are also other structures that can develop. There's shocks that can develop. There's maybe rarefaction. There's all kinds of things that can develop. My understanding is that this basically is an expansion in some kind of asymptotic states of hydrodynamics. And the bit about diffusion is the two-body asymptotic states. You have like waves that can come from very far and then scatter and go, and then you look at some kind of a matrix element in these asymptotic states. But if you have a system which is not integrable, they are not linearly degenerate, there are other objects that can develop like shocks. And probably there's a bit of this diffusive Hilbert space that corresponds to shocks, these shocks. And then they will be corresponding to different, quadratic, different charges, linearly extensive with respect to H prime, different charges which encode this shock structure. And I suspect that this is what is related to the noise that we add usually in fluctuating hydrodynamics, where we have diffusion constant plus noise. That noise must correspond to this other bit of the Hilbert space, and probably associated with shock structure in hydrodynamics. Yes, indeed, there's this relation, and so it's not completely, if we add it by hand, you have to connect it in some way, and that's because it has a physical origin, which is from this additional bit of the Hilbert space. I think.
Are there any other question? So let's thank Benjamin again for a very interesting talk. And